So the goal of our experiment is we want to know what happens to the bed of a gravel bed river, what happens to the bars in the bed of the river as you change what comes into it, or the sediment that comes into it. By sediment, we mean the sand and the gravel that normally works its way down a river. So what we're doing in this experiment is we've got this really nice, almost 3-meter wide channel, and we can build a river inside of it. And unlike a lot of flumes where you need to scale everything down, you need to make a sort of a mini river, we can make an actual river that is of the same size and works and acts like close to like a real river would outside. And then we ran the flume, so we know from our predictions and calculations that if you run at a certain amount of water at a certain depth for a certain amount of time, we should see the bed sort of organize itself into these big gravel bars, just like you see on a big gravel river. And then the experiment is what happens to those when you add extra sediment into it. So we take all this 20 cubic meters of sediment that we've reserved, we put it on a conveyor belt, and we dump it in the river at very careful and measured rates, so that we get our desired upstream sediment supply. And the question we're asking is what does the river do with it? How does it put it? Where does it put the sediment, and why is it going there? And then in the end, what does the river look like? So does it look much different than it did in the beginning before we dumped all the sediment into it? In this flume, one reason why it's really nice to work here, one advantage this has over real rivers, we have this, what we call our magic cart. So it runs up and down on these little tracks, and it can measure the water surface and it can measure the bed surface very, very accurately. So it takes very detailed surveys. And what we can do with those then is we can take, each evening we take a really nice a detailed survey of the bed, and we can compare those over time and tell the story of how the bed of the river evolved. We want to understand how gravel bed rivers work. We dam up the rivers, we store it, we dole it out for drinking water, for irrigation water, we use it for power. And we know that as we put those dams, as we dam up our rivers to use that water, we know that affects both the water and the sediment that comes down the river. And as you alter the balance of the river and the sediment that's coming down the rivers behind some of our really big dams, the rivers change. We don't necessarily like that because we like to look at gravel bars and they're pretty nice places to go fishing. And one reason why they're a really nice place to go fishing is the fish also like them and the insects that the fish eat. So having that topography in a sort of gravelly mountain stream is fairly important for us. So there's some places we know that we don't have that topography where we'd really like to have it. So one solution is, there's been pursued some places to take the dams down. My field research sites is on the Sandy River out where they removed the Marmot Dam on the Sandy River in Oregon, just off of Mount Hood. And when they took that dam down, they had this gravelly mountain river, and then when they pulled the dam out, there was this whole big plug of sediment sitting there. So all that sediment gradually worked its way down the river, and as it did so, it altered the effects of the topography downstream. Understanding how that river digests that extra sediment that we give it, and where it puts it, and how it configures the bars, and then ultimately what the fish and the insects do with that new bar and topography is something that we're interested in. But then we took the opportunity then to come into the unique opportunity, I guess, to come into the main channel here at the St. Anthony Falls lab and run an experiment basically simulating what we're doing for real on the big rivers or on the dam-influenced rivers, measuring how the riverbed changes as we dump a whole bunch of gravel into it.